Super 8.
It's going good. We were diverted to Celsius and Kelvin. John, did you use 4.5 or would you mind no? It's kind of filled with my brain. It's just the basic.
After the break, you want homework?
We have to do today's lunch.
Huh? Oh, that's not. We still haven't done today's lunch.
Correct, but it's a short one.
Okay.
So
That was really sad.
the gas law lab is, the gas law lecture is very long. It's designed to be kind of 1.5. But today's is very short.
Alright, awesome.
What do you mean it's very short? Did we get out earlier or something? Earlier than we
I think today's lecture plus what we did,
Okay,
sort of a
you know.
normal, maybe a little bit shorter. There really isn't a whole lot to go over today.
There's no issue, I'm just asking.
There are 21 slides for today. One of them is the title slide.
Oh yeah. Thank you.
Where's the drill number? If anything goes wrong. Oh, no. There's like 6 holes in my bed. You put that one in? I don't know.
Okay.
I write them coded via. I had to. That's proof. Is that a picture of mine? Video?
This is what I look. started one. And then I went to the jump house, trampoline house. When played basketball.
Is that a game school?
It's a new one.
What's it called?
Yeah. But when I went, it was
Do you play basketball?
it looked like a cool field.
They have a, there's a basketball court?
No, in my neighborhood it's basketball. Like,
Okay. How much is it? $13. Where's it at?
it's on 13. The trampoline.
It's like 10, 15 minutes from here. They could go to my house, like, you go a minute past, why am I just not finding how to, it's for free, what is? Is it worth it?
It's pretty good. It's different things. It's not just, oh, I'll use trampoline. It's like 30.
They have courts, like emergency charges, or like intermittent courts. I want Durham. They have monkey bars, I want Durham there.
There's like a bouncing dodgeball one too.
Dodgeball, what is it? Oh, they have dodgeball. Take a direction.
Like while you play dodgeball, you gotta bounce.
That sounds so fun.
And there's like ramps where you also jump on.
You need help. You don't have legs and then go on there.
And you can jump pretty high, dude. Like for real. You can like run and
Like how high? 6, 7 feet?
you can jump as high as you want, but I just don't like getting too high because it's so cool.
You're not home crashing or something.
There were little kids all over the place.
But not in the back. In the back, it's all walls. How big is it? A warehouse.
It's pretty large.
Go there for a second. Kmart. Go there.
It's basically like half this building, maybe a little more.
It's pretty big. No. Like an adult bought it, like can this get lost? If they bought it, yeah. That one's all have one of those things. Like bed, you bought, you plan on it, you know, like you can bought it. Yeah. They're getting them.
Yeah, there's like phones,
You'll love it. 20 years old. What's it called? You have to buy your socks.
The thing is, you can't wear shoes.
You have to wear their socks if they have like a little creepy on the wall.
So you don't slip off and leave your head out on the hot place.
Those ankle socks? No. Fine.
It's like,
No show.
yeah, I thought they were no.
Good finish.
It's like a membership too.
We're telling Gary we're gonna go see there. Tell me what I'm looking at. That'd be good one.
You know, the car was yeah, maybe that's what I do.
When I went to see the big guy, he didn't know turn around. So he asked me if we could share. They're here to buy.
We took the,
Purple?
we took the $10 Amazon
What'd you do?
and then refill.
I know. The chemistry.
It's too carby. It's too like,
I could hardly breathe. It was so
really just, look up.
No.
Probably too much.
weird, like $80 a piece. They're literally like 14 rounds. And he kept messing with me.
But it's greasy. It's like,
Yeah. It's like,
that would be like $13. I would pay like $13 worth of fish.
yeah. I typically get it because
The meatballs weren't too bad, but I thought it was gonna be so much.
the people are nasty. That's right there. It's all about
we finished our gases. And believe it or not, there is a whole lot more that we could have talked about with gases. Gases do a lot of things. And that's because the molecules, the atoms, are far apart and they fly around. Liquids and solids aren't nearly as interesting. They don't do a whole lot. And so we're going to cover pretty much everything there is to cover for liquids and solids in 21 slides. So what we're going to talk about for liquids and solids, some of it you already know. Right? The first week of class, we talked about the different states of matter. So based on what you know about different states of matter, which of these cats is a solid cat, and which one of these is a liquid cat? Which one's that one? That one. Why is that one a liquid cat? It took the shape of the container. That one is a solid cat. It is very rigid. I don't think it is dead. I think it's just sleeping.
Stretching.
Or stretching, maybe just stretching.
No, it's definitely sleeping. Its head's down. It's like.
But it's not taking the shape of its container, right? Its legs are up off of the bed. So we know that solids and liquids. With solids, there's a definite volume. So we're not going to be changing the volume of our solids or our liquids. But with the solid, there is a definite shape. The shape doesn't change. But with the liquid, the shape does change. So how did we describe, how did we explain those properties at the molecular level? Why does neither one have, why do both have a definite volume? Why does the volume not change for solids and liquids?
Because the molecules, they stay together.
Right. In solids and liquids, the molecules are so close together that you can't really compress them. I mean, they're so close together that there's very little room to compress them. And if you pulled them apart, they'd become a gas. And so you can't really compress or expand solids and liquids. Why does a liquid take the shape of the container, but a solid does not? At the molecular level.
The liquid, like motile, move a little bit.
Right. You remember, in both solids and liquids, the molecules are close together, but in the liquids, they're moving around each other. In a solid, they just sit in place and shake. Think if you took a sugar cube, that's one chunk, right? The grains of sugar in there are stuck together. And so the cube stays a cube. But if you took the same amount of sugar, when it was just granulated sugar, and you set it on the table, would it stay a cube shape? No. Because all the particles move around each other, it's going to take a different shape. So, same thing happens at the molecular level with the solids and liquids. You can recreate those atoms that move around each other at a real life scale by using grains of salt, sand, or sugar. It's going to act the same. You just have to think of the molecules acting at the molecular level. So the first thing we're going to talk about is what we're going to call a liquid-vapor equilibrium. Have we used the term equilibrium yet this semester? No. Okay. So you know that if you put a liquid on the table in a glass, it's going to evaporate, right? You know if you put, let's say, a closed water bottle on the table and let it sit there, then you're going to get condensation up at the top of the bottle, right? What's going to happen in that bottle is what we call an equilibrium. In equilibrium are two processes that are direct opposite of each other, like they undo each other, happening at the same time. And so if you have that bottle of water sitting on the desk, you have liquid water in there that's evaporating. It's going from a liquid to a gas, but also, at the same time, there is gas in there that's going into the liquid form. The evaporation and condensation are happening at the same exact time. Initially, one of them is going to happen faster than the other. I mean, if you start with a bottle, initially there is no water vapor in there. And so there is no vapor to go from gas to liquid. And so you have liquid to gas happening, but no gas going backwards. The more liquid becomes a gas, now you have more and more gas. As you have more gas, more of it's going to go back to a liquid. So when it hits a happy place, that both processes are happening at the same speed, meaning the same amount of liquid is becoming gas as gas is becoming liquid, that is called equilibrium. The amount of liquid, the amount of gas are not changing. At the molecular level, they're still going back and forth. But the same number of molecules are always in the liquid state, and the same number are in the gas state. Which specific molecules they are is going to change, but that ratio will not change. So here's a flask. We've got it stoppered, and there's water in here. Initially, we just have liquid water. After a little bit of while, one water molecule evaporates. It's now up here in the gas state. After a little while longer, we get another one, and then another one, and then another one. But now, we waited longer, and we still have 4. We went from 0 to 1 to 2 to 3 to 4 to 4. As they're flying around, if this water molecule flies and hits the water down here, it's going to stick down into the water. It's going to leave the gas and go back to liquid. And so it makes sense that the more molecules you have flying around up here, the more often one of them is going to hit the water, right? And so continuously, water molecules are going to come out of the liquid up into the gas state, and they're going to evaporate. But eventually, you reach the point that the same number are coming out as are going in. So if we let that sit there in a sealed container forever and ever and ever and ever, there's always going to be 4 in the gas state. That's an equilibrium. And if you measure the pressure exerted by that gas when it's at equilibrium, we call that vapor pressure. So vapor pressure is the first thing we're going to talk about in terms of liquid. Property is the word I'm looking for. Vapor pressure is the first property of liquids we're going to talk about. If you set a liquid on a bench in a sealed container, it will evaporate until it reaches this equilibrium. And the amount of gas in there will always be the same amount if you're at the same temperature. The temperature will change the amount up here, but if you're at the same temperature, the amount in the gas phase will always stay the same. And the pressure of that gas up there is called the vapor pressure. So if you close a bottle of water, the water is going to evaporate into the gas phase until you have enough gas in there to reach the defined vapor pressure of water at that temperature. And there are tables that have this information. So if you look up the vapor pressure of water at a certain temperature, the water in that bottle will evaporate until in that empty space at the top of the bottle, there is enough water vapor to give that pressure. And so this is related to boiling point, because the water is evaporating, right? And water evaporating is very, very, very similar to boiling. Boiling happens very quickly. Everything is at a temperature that makes it want to go from liquid to a gas, so it's going to happen very quickly. If you set it out here not at boiling temperature, it will still evaporate. But it will only evaporate until it hits that vapor pressure, and then it will stop. If you're boiling something, it will just keep going and going and going and going and going. So this is a graph showing vapor pressure and temperature for 3 different compounds. Okay? So on the x-axis here we have temperature. It's in Celsius. Basically, to the left is cold, to the right is hot. Then up here we have vapor pressure in atmospheres. So what this is really telling us is how much and how quickly this liquid is going to evaporate sitting there on the bench. Okay? So if we look at this one's methane, that's methanol, and this is water. And so at this point, atmospheric pressure, remember, is 1 atmosphere. The normal pressure in the atmosphere is 1. And so in order to be 1 atmosphere, methane only has to be, looks like, negative 180 degrees Celsius. What do you know about methane at room temperature? What state is it?
Yeah.
It's a gas. Because room temperature is way up here. The further up this line you go, the more of the methane is going to be gas. And so we are way off the scale. You have to get methane really, really, really cold, at least at room temperature, to get it to be a liquid. Over here you have methanol in water. What do you know about methanol and water at room temperature? What state are they?
Liquid.
They're both liquids. What do you know about how quickly alcohol, methanol, evaporates compared to water?
Fast.
Faster. Alcohol, when we talk about alcohol, it's generally ethanol, but ethanol would be right next to methanol here. Alcohol evaporates quicker. At room temperature, let's say, I guess this would be 40. So over here, this is about room temperature, this first dot here. In this case, methanol has a vapor pressure, right? Water line isn't even drawn yet. If we follow this down, it would be almost nothing. And so at room temperature, water takes a long time to evaporate. Methanol, though, will evaporate quicker. What this is telling us up here is that when you raise the temperature of something to the point that the vapor pressure is equal to the actual atmospheric pressure, then it boils. And so with water, if we raise the temperature to the point that the vapor pressure equals 1 atmosphere, this is the boiling point of water, which is 100. Methanol boils at just over 60. Methane boils at negative 160. Really what you need to take from this is just that different compounds, different different compounds, different elements, different gases, different liquids are going to have different vapor pressures. Each one is going to have a different propensity to go from a liquid to a gas. It's going to evaporate different speeds sitting on a bench at room temperature. And that's because the intermolecular forces are different in each compound. So we have intermolecular forces and intramolecular forces. Intra means internal, within a molecule. Those are our bonds, the ionic covalent bonds. Intermolecular forces are forces between molecules. So remember the last slide of our gases, we said when they're really close together, we have attractions between them. But in liquids and solids, they are permanently right next to each other. So these attractions are very important in liquids and solids. They are always there. This explains why some compounds are gases at room temperature, some are liquids, and some are solids. If you have strong forces holding them together, they're going to be solids. If they're very weak forces, then the molecules can just fly apart. And that's going to be a gas. Also explains why different liquids have different boiling points. If you're boiling something, a higher boiling point means you have to put more energy into it in order to get it to go from a liquid to a gas. You have to put more energy into it to make the molecules fly apart. If you have stronger forces holding them together, you're going to have to put more energy into it to break that force. Also explains molecules sticking together in the liquid state. We'll talk more about some examples of that. These are attractive forces. We're not going to talk about repulsive forces, just attractive forces. And they are called intermolecular forces, and they are between different molecules. We have three types of these forces. We have London dispersion forces, what we call dipole-dipole forces, and hydrogen bonding. We're going to talk about each one independently and get through them. So the first one are London dispersion forces. These are the most common, but also the hardest to understand. Okay? So number one, before I even put anything up here, I want to say that every compound in every element has London dispersion forces. A type of problem you're going to deal with these liquids and solids is which forces are present in a certain compound. And so you're going to have to figure out whether they have dipole, dipole, or hydrogen. But they will all have London dispersion forces. Okay? Everything has London dispersion forces. And that's because London dispersion forces come from electrons. If there are electrons, there are London dispersion forces. And you certainly can't have an element or a compound without electrons. And so everything is going to have London dispersion forces. So up here, in A, we have two atoms. In the center, we have the nuclei, and then outside that, we have the electron cloud. We like to draw that cloud as a sphere. But the electrons don't fly around in that cloud in orbits. Remember, they don't travel like planets around the sun, they fly around. And with orbits, or with orbitals, all we know is that the electron is somewhere in that orbital. It could be over here, it could be over there, up there, or down there. We don't know. And so if you have multiple electrons flying around in that orbital, in some cases, they're both going to be, so let's say they're two, in some cases they're both going to be on the same side. They're moving around randomly. On average, over time, they will spend an equal amount of time everywhere. But at one point in time, it's possible for them both to be on the same side. And if they're both on the same side, our charges are going to be off balance. Remember, the nucleus is positively charged. The protons are there. The negative charge in our atom comes from the electrons. If we have more electrons on one side than the other, one side is going to be more negative than the other. The more electrons you have in an atom, the more out of balance they can be. If you only have one electron, you can only be out of balance by one. But if you have 100, it's possible for all 100 to be on one side and 0 to be on the other. And so as we go down, the cloud here is going to get more and more distorted. On this side, there are more electrons than on that side. If there are more electrons on that side, it's going to become negative. But it's not a complete negative. It's going to be a partial negative. This is a lowercase delta, and that's a partial negative. Just like when we had our polar covalent bonds, we said one atom is partial negative, one atom is partial positive. In this case, within an atom, one side is partial negative, one is partial positive. Now imagine you have two atoms right next to each other that do it at the same time. Now we have a partial negative right next to a partial positive. That's going to cause attraction. And so we now have attractive forces between those two atoms. Up here, they are both completely neutral. They sit next to each other. They don't even know they exist. But at this point in time, in this little snapshot, they're both warped, and they're warped in the way that the negative is next to the positive. If they were warped to the way, the point that the negative was next to the negative, there would actually be repulsive forces. But here, the negative is next to the positive, and so they're attracted to each other. Okay. Sometimes I see that people have a hard time picturing this whole random movement of electrons, and some of them are going to be on one side, and others are going to be on the other. So, how many of you, or is there anyone who when they were little or currently has little fuzzy rodent pets? Like mice or let's say moles, yeah. What do you have? One guinea pig. Okay, let's say you have 100 guinea pigs. Okay. Let's say you have 100 guinea pigs, and those guinea pigs are negatively charged. Okay? And you dump them in the center of this room with all of us in here. What are those guinea pigs going to do? They're going to run. And they're going to run randomly. So we're going to dump 100 in the middle, and they're going to start running all around. In a perfect world, if you took a picture of the room, there would be 50 on the left, 50 on the right, 50 in front, 50 in back, no matter, depending on how you want to split the room up. But in reality, it's not going to be equally divided, right? You may have 75 up front. More likely, you'd have 75 in the back where there are no people, and 25 up here hiding in your backpacks. It's not going to be even, though. But if they're negatively charged, and you have 75 in the back and 25 in the front, there's going to be more negatives in the back, right? And so the electrons move just like that, randomly. Over a large period of time, it all evens out. But at one point in time, everything's off the table. They can be anywhere they want to be. And so because they're completely always flying around, these little warped electron clouds are constantly happening. As soon as they happen, they go away though. They're there and they're gone. Because this one is like this, but the next zeptosecond, it's flipped the other way. But there are so many atoms in our sample that there's always some that are like this. It's such a statistical anomaly that it's never ever going to happen that none of them are like that. And so these London dispersion forces are always, always present. They're present in nonpolar substances. They're present in polar substances. If it exists, it has London dispersion forces. So this explains why different halogens are at different states at room temperature. So chlorine at room temperature is a gas. At room temperature, bromine is a liquid. At room temperature, iodine is mostly a solid. Remember, we've used iodine in lab multiple times at this point. It's a chunk. It's a solid. Chlorine, though, is a complete gas, and bromine is a red liquid. You can see some of it down here. And so the question becomes, why are they different states? If you look up here, you have chlorine, bromine, and iodine. What can you tell me about the number of electrons in chlorine, bromine, and iodine? Which one has the least? Which one has the most? Chlorine has the least, iodine has the most. The more electrons you have, the more distorted your electron cloud can be. The more distorted it is, the stronger the attractions. And so, essentially what this means is the heavier your compound, or your element, or whatever you're dealing with, the stronger the London dispersion forces. Find the molecular weight. The thing that has the larger molecular weight will have stronger London dispersion forces. So we're going to say iodine has the strongest forces. That's why it's a solid. There's strong forces holding these iodine molecules together. There's an I2 right next to another I2. In order to pull them apart, to make them a liquid or a gas, you have to put energy in. With bromine, though, those forces aren't quite as strong. So at room temperature, we've already overcome them enough to make them a liquid, but not enough to make them a gas. In chlorine, they are so weak that at room temperature, it's already a gas. And so fluorine is even weaker. And astatine is even stronger. So if I give you two compounds and ask you which one has the stronger London dispersion forces, all you have to do is look at the molecular weight. So which one is stronger, helium or krypton? Krypton. Krypton is bigger than helium. What about hydrochloric acid, HCl, or hydrobromic acid, HBr? HBr, hydrobromic. What about methane or C2H6 ethane? C2H6. It's bigger, it has a larger molecular weight, it has stronger London dispersion forces. Now taking it one step further. For CH4 or C2H6, which one is going to have the higher melting point? Think about why C2H6.
It's going to have a higher melting point because it's also a higher point to be able to get to
Right.
become a gas.
Right.
So it just makes sense.
The same forces that are preventing it from going to a solid to a liquid are the same ones that prevent it from going from a liquid to a gas. The C2H6 has stronger London dispersion forces. They're stuck together stronger. And so to get them to melt, remember when you go from a solid to a liquid, they move apart just a little bit. You're going to have to heat it up more. It takes more energy to overcome the stronger London dispersion forces. Which one is stronger, CH4 or SiH4? SiH4. Because the silicon is heavier than the carbon, which makes this heavier than that. Okay, that's London dispersion forces. The next one are dipole forces. Dipole forces are very similar to London dispersion forces. It's the same idea going on. It's just that they're permanent. And because they're permanent, every atom in there is going to have them. And so as a sum total, there's going to be more forces. Because with the London dispersion forces, they only exist for that split second for a small proportion of your atoms or your molecules. With dipole forces, they are permanent. So every molecule is bonded or attracted to every other molecule in your sample. So this is only going to work for polar molecules. So this is a polar molecule. And this is showing us that in this polar molecule, it looks like the red atoms have more electronegativity. If they have more electronegativity, they're going to have a partial negative. So the yellow one on this side is going to have a partial positive. And those are always going to be there. And so you put two of them next to each other, arranged correctly, and you have, again, a partial positive next to a partial negative, which causes attraction. Not only are these permanent, which makes them stronger, but these partial negative and partial positives are also more negative, more positive than the London dispersion forces. And so even at a split instant, this attractive force is going to be stronger between just two, because that's more positive and more negative, which creates stronger attraction. So remember, this is only in polar molecules. So figure out if something has dipole forces, look at it, figure out if it is polar. In a lot of cases, it will be obvious. In some cases, not a case I would be likely to give you on a quiz or an exam. You would actually have to do the Lewis structure, the parent structure, and the molecular shape before you can figure it out. Okay? But you have to, one way or another, whether you can look at the formula and figure it out or not, you have to figure out if it's polar. If it's polar, it has dipole-dipole. If it is non-polar, it will not have dipole-dipole. It's called dipole-dipole because this is called, I almost flipped you off there. Did anybody catch that? No, good. I almost pointed with my middle finger. That is called a dipole, okay? If you have a partial negative, partial positive, that's dipole. So that's a dipole. So the attraction between a dipole and a dipole is what? A dipole-dipole attraction. But a ching, nobody laughed. So this is SO2. It is polar. Remember, this is SO2. It's shaped like this. Do you remember what CO2 looked like? It's not the same thing.
Is it a straight line?
It's linear. And so with CO2, you have that. Is that polar?
Nope.
No, it's not. So you can't just look at the formula and tell whether it's polar or non-polar in some cases. Usually, I would give you one that is just, you look at it and it'll be obvious.
Like water?
Well, no, water is actually not obvious. Yeah.
So CO2 is like rods stacking up on each other?
It's linear, yeah.
But like,
So,
not just one.
some are going to be like that, some are going to be like that,
Oh.
some will be like that. But within a molecule, there's no partial negative, partial positive. And so no
I'm
matter
thinking-
the orientation, there's going to be no attraction.
I'm thinking like solid all of a sudden, I'm sorry.
Yeah, so you're talking when it makes a crystal.
Like carbon.
Different compounds are going to make different crystal structures. That's not something I've dealt with in a long time. That's not something.
Okay.
So, looking at these, will A have dipole-dipole forces? Yes. How do you know?
Because it's SO2.
Because it's SO2, we just talked about it. But it is polar. It is not symmetrical, right? We have reds on this side, no reds on that side. It is not symmetrical, so it is polar. If it is polar, it has dipole-dipole. Does that have dipole-dipole? Yes. There are greens on the bottom, whites on the top. It's not symmetrical. What about C?
Yes.
Yes. The greens are more towards the bottom than towards the top. It'd be easier to see if they were smaller. So, but in this case, the greens are actually more towards the bottom than the top. What about D?
No.
No. That is symmetrical. In this case, the greens are arranged around the center of the brown one. That's trigonal planar, that's trigonal pyramidal. So you have to figure out whether it is polar.
What do you call B again?
B was polar. So
No, the shape.
oh, that would be, it's tetrahedral, but two of them are chlorines, two of them are hydrogens.
How do you know what? Oh. I was like, what? You're just making stuff up right now? Like.
We don't have that on the test, do we? Like
Pictures, no. So I was waiting to see if I had a slide, but what you would see on an exam is just a formula. And so most likely I would give you a formula that you look at it and there's just no way it could be questionable. You look at it and say that's polar, you look at it and say that's non-polar. So, as an example, what if I gave you H2? Is that polar? No. It's the same element. If you have all the same element, it's non-polar. What if you had nothing? CH4.
non-polar.
Non-polar, why?
Because the hydrogens are all the way around.
The hydrogens are all the way around, and carbon-hydrogen was that exception. A carbon-hydrogen bond is actually a non-polar bond. So all of the bonds are non-polar, and so it is non-polar. What about CCl4. These are polar bonds, but the chlorines are equally spread around, and so it is non-polar. What if I had SiCl2Br2? That's polar. There's no way you can arrange two chlorines and two bromines in such a way that it's going to be symmetrical. Okay. So an ionic bond is essentially an extremely strong dipole. I mean, it is so strong, instead of being a partial positive and a partial negative, it is a complete positive and a complete negative. That's why ionic compounds have high melting points. They have very, very strong attractive forces. And what you need to remember here is that the larger the charge difference between the two ions, the stronger the force. So, we got an example here. Magnesium oxide and sodium chloride. We're going to see what I mean by the difference in charge. The charge, how big the charge difference is. Let's look at magnesium oxide. What is the charge on the magnesium ion here?
2 plus.
2 plus. What's the charge on the oxygen ion? 2 minus. What's the difference between them?
0.
Think of a number. Think of when you're in first grade and they have the little number line sticker
4.
on your desk. 4. Thank you. These are 4 apart from each other. Let's go to sodium chloride. The charge on sodium is +1, or 1 plus. This is 1 minus. What's the difference between them? 2. This one has the larger charge difference, and so the forces between magnesium oxide are stronger than the forces between sodium chloride. Just figure out what the different charges are, how far apart are they. The further apart they are, the stronger the attractive forces.
So add up the absolute values of their charges.
Yes, you can do that. That's one way to think about it.
Bless you. Thank you.
Okay. Our last type of intermolecular force is called hydrogen bonding. So if you look at boiling points, a table of boiling points of different compounds, some of them are not going to make any sense. So water is one of them. Generally, with dipole-dipole, we said the bigger the molecule, the stronger the force. So generally, bigger molecules have higher boiling points. Water is very small. Water is polar, but it's not super, super polar. But water has a very high boiling point, and it's because of hydrogen bonding. And to have hydrogen bonding, you need to have hydrogen bound to nitrogen, oxygen, or fluorine. A hydrogen bound to any other element does not count. It has to be a hydrogen bound to a nitrogen, an oxygen, or a fluorine. And the only way I have to help you remember that is that nitrogen, oxygen, fluorine. They're right next to each other. Other than that, there's no good way of remembering that. If you have hydrogen bonding, that is very strong. And so something that has similar London dispersion forces to another molecule, similar dipole-dipole forces to another molecule, but has hydrogen bonding, is going to have a much, much, much higher boiling point. This is what we're talking about in terms of hydrogen bonding. So this is water. Think of hydrogen bonding as sharing hydrogens. So here are 5 water molecules. That oxygen is attracted to these hydrogens on the water molecules next to it. The hydrogens on this water molecule are attracted to the oxygens on the water molecules next to it. So you get this big network of fake hydrogen bonds. They're not actual bonds, they're attractive forces that hold these together. And as long as you have hydrogen with a nitrogen, oxygen, or fluorine, it will work. Ammonia in water has hydrogen bonding. Water has hydrogen on oxygen. Ammonia has hydrogen on nitrogen. So in this case, there's hydrogen bonding between the ammonia and the water. There's also going to be hydrogen bonding between that water and that water. Over here we have just ammonia. The ammonia is hydrogen bonding to itself. And here is hydrogen fluoride. That's the hydrogen bound to that fluorine. That hydrogen is bound to that fluorine, and you get the zigzag pattern. If you have hydrogen with a nitrogen, oxygen, or a fluorine, you will have hydrogen bonding. If you have hydrogen bonding, you have the strongest intermolecular forces possible. Hydrogen bonding is what holds our DNA together. Now think about this. Why is hydrogen bonding so important in DNA?
It provides shape.
It provides shape. So we need a very strong bond, right? Dipole, and London dispersion are not going to cut it. We need to hold that double helix together. But even though hydrogen bonding is strong, it's not as strong as a covalent bond or an ionic bond.
You still need to be able to take it apart.
You need to be able to take it apart, yes. And the double helix has to peel apart in order to replicate your DNA, in order for your cell to divide. And so a hydrogen bond is strong enough to hold it together, but weak enough to be broken when it needs to be broken. And so these are the nucleotides in your DNA. Remember, there's adenine, thymine, cytosine, and guanine. And so this explains why they always pair up in the same way. It's always A and T and C and G. If you look at the molecules that make up those nucleotides, C and G, they made this, I don't know whether they got it wrong or just someone was looking at it weird, but cytosine and guanine are actually these two. Adenine and thymine are these up here. But cytosine and guanine have 3 hydrogen bonds. A and T have 2. So if you try to put one of these with one of these, they don't go together right. And so that's why they always pair AT and CG. Also, if you have part of your DNA that has more CG pairs than AT pairs, it's actually held together stronger. So when I do things with DNA in lab, I have a little machine that just changes the temperature of it. And I do reactions. I make DNA in lab. When I make DNA, I have to pull apart that double helix. So I calculate, based on what percentage of my DNA is CG, what percentage is AT, I know what temperature to set my machine at in order to get it to pull apart. If you set it too high, things can just break apart and decompose and fall apart. If you don't set it high enough, nothing ever comes apart, and so you can't replicate it at all. So let's look at some of these. With number 1, have hydrogen bonding.
No.
Is there a hydrogen bound to a nitrogen, oxygen, or a fluorine?
Yes.
Yes. These hydrogens are on that nitrogen. In this case, a lot of times you need to look at the formula. The formula is going to tell you which atoms are bound to which atoms. In this case, those hydrogens are on that nitrogen. If you ever see a formula and you question, are these hydrogens on this atom? You can always ask me. I will tell you yes or no, but it's then up to you to interpret, does that mean it has hydrogen bonding or not? Okay. What about number 2? Does that have hydrogen bonding?
Yes.
No.
No.
There's fluorines and nitrogens, but there aren't even hydrogens there.
Oh.
You have to have a hydrogen on a nitrogen, fluorine, or an oxygen. What about number 3? No. There are hydrogens, there's an oxygen. But the hydrogens are not bound to the oxygen. The hydrogens are on that carbon, they're on that carbon. There are no hydrogens bound to that oxygen. What about that one?
Yes.
Yes. In this case, these hydrogens are on carbons, but that hydrogen is on an oxygen. This is ethanol, which is the alcohol that you possibly drink if you're old enough. Some of you probably aren't, are you?
Most of us probably aren't, but it doesn't sound.
I guess we were all there at some point at work. Here is HCl. Does that have hydrogen bonding?
No.
No. Hydrogen, but there is no nitrogen, oxygen, or fluorine. So this is a way to look at it. Remember, everything has London dispersion forces. If it exists, it has them. You then have to figure out, does it have dipole-dipole forces, and does it have a hydrogen bond? Some will, some won't. For the most part, if it has hydrogen bonds, it will also have dipole-dipole. It would be very unlikely for you to come across a molecule that had hydrogen bonds but did not have dipole-dipole forces on a quiz or an exam. To me, that would be a trick question. That would be above and beyond what we're trying to get out of you. But it is possible, just fair warning. So, everything has London dispersion. If it is polar, it has dipole-dipole. If it has hydrogen on fluorine, oxygen, or nitrogen, it has hydrogen bonds. So my suggestion would be, look, first thing I would look at, does it have hydrogen bonding?